Hello, here's a screencast for section 5.5 to 5.7. 5.5 is on the collision model, and the learning objective is explain the relationship between the rate of an elementary reaction and the frequency, energy, and orientation of molecular collisions. So, kind of talked about this a little bit before. These are factors that affect the reaction rate. Basically, to make a reaction go faster, you want to increase the number of effective collisions. So an effective collision is when the colliding particles have enough energy to overcome the activation energy barrier. So the more often the particles collide, so that's the frequency, and the faster the particles are moving, which leads to a higher kinetic energy. And if the correct part of the reacting particles hit each other, that's the orientation, then you have an effective collision. Now, you want to know that most collisions, for most reactions, most collisions are not effective. So most of the collisions don't result in a product. So it's usually a smaller number. Over here is a example of the correct orientation. This is carbon monoxide reacting with oxygen. And for the reaction to occur, you have to have the carbon part of the carbon monoxide hitting the oxygen molecule. And that results in an effective collision if they collide with enough energy. If you have the oxygen end of carbon monoxide hitting the oxygen molecule, then no reaction occurs. Okay, and then this also leads to Maxwell-Boltzmann distribution. That concept is when you have higher temperatures, you have a wider distribution of particle speeds. So in the red you have, this would be the hot, higher temperature. In blue you have a colder temperature. So at colder temperatures it's a narrower distribution. And you can relate this to effective collisions if we say that, at this speed, draw a line. Oops, sorry. Let me just start over. Draw a line right here, okay? So at that speed, that's where the particles have enough kinetic energy to make an effective collision. So at higher temperatures, you can see you're going to have a greater number of particles that have enough kinetic energy to collide and turn into products. At lower temperatures, you don't have as many effective collisions. So the way to increase the reaction rate is to get a greater number of effective collisions. All right, the next section is 5.6. That's reaction energy profile. So the learning objective here is represent the activation energy and overall energy change in an elementary reaction using a reaction energy profile. And this is the essential knowledge is just understanding this energy graph. And you'll also see this in Unit 6. But really for this unit right now, this is kind of the important part. This activation energy, that's the energy barrier that needs to be overcome to get from reactant to product. So the vertical distance from, this is potential energy on the y-axis, from the potential energy of the reactants to the top of the activation energy barrier, that's the activation energy for the forward reaction. We can also talk about if it's a reversible reaction, the distance from the potential energy level for the products to the top of this hill, that would be the activation energy for the reverse reaction. So in this case, the reverse reaction would have a greater activation energy. You also want to know at the top of this hill is what we call the transition state, and that's just a state in between the reactants and the products. And we'll see this in Unit 6 too, but the overall energy difference between reactants and products, that's going to be the energy change or the enthalpy change for the reaction. But we'll talk about that more later. And the last section for today is 5.7 on Introduction to Reaction Mechanisms. Now, we have a few sections on reaction mechanisms and some of the things we do with them. In this part, the learning objective is just identify the components of a reaction mechanism. So the essential knowledge is, first of all, understand a multi-step mechanism is where it takes 2 or 3 or 4 steps for the reaction to go to completion, to go from reactants to products. Most reactions occur this way, so they end up with multi-step mechanisms. All right, so one of the first things you want to be able to identify is an intermediate. So an intermediate is something in the mechanism that is produced in one step and then is consumed in a later step. So an intermediate is a product in an earlier step and it's a reactant in a later step. So in this case, we have HI. It's a product in this first step and it's a reactant in the second step. All right, and then you also want to know, identify catalysts. So catalysts are things that speed up chemical reactions but don't get consumed, and we'll talk about those in the next screencast also. But a catalyst is something that is a reactant in an earlier step and it's a product in a later step. So in this case, in this mechanism right here, yep, the iodide ion, it's a reactant in the first step and a product in the second. And this mechanism also contains an intermediate, this IO negative. It's a product and then a reactant. So IO is an intermediate, whereas iodine is a catalyst. Okay. Then the last thing you want to be able to write out from a mechanism, what's the overall equation? So we want to put all the steps together, in this case it's only 2, into one overall reaction. Intermediates and catalysts do not show up in the overall equation. They end up canceling out. So the iodide and IO negative, those cancel. And then we combine like terms on the same side of an equation. So we have these 2 H2O2, so we put those together in the overall equation. So 2 H2O2. So we just have a single reactant. And on the product side, there's a water in each of the steps, so we put those together, coefficient 2. And then we also have oxygen, O2. So we want to be able to put all the steps into one equation. Right? And that's all for today. Have a great day. Bye.